Okay, good morning, everybody. First, a few announcements. I posted the homework solutions last night. I also posted a MATLAB script that we will talk about today that hopefully illustrates some of coordinate transformation and rotations. So I might update this. I worked on the comments in the MATLAB script this morning to make them a little bit more consistent with my explanation that I will provide later on. One issue that I ran into before we scheduled the office hours, students that do their prelims in the department. Currently, the prelims is one step towards doing your PhD. It's another kind of comprehensive exam. They scheduled this way ahead in early August before we scheduled our office hours. And so I have a conflict this afternoon. During the office hours, I have a prelim. So I can offer you, stop by any time between, 11 and 1. And then I have, unfortunately, these prelims coming up this afternoon. If you want to catch me tomorrow, please drop me an email, and I will accommodate, if you have any questions. That will, I think, happen next week again. But again, that was unavoidable because they had to schedule their oral part of the prelim way before we even thought about this course. OK, so the last time we talked about the stress tensor in 2D. And that is something that I'm pretty aware that most of you had in your undergraduate program. And today we want to talk about the full beauty of the stress tensor, so the 3D stress tensor. And obviously, that's not anything conceptually different from the 2D. We add a third dimension. However, for example, the method of Mohr circle is not directly applicable anymore. And also the idea of deriving the stress transformation by doing equilibrium considerations is still possible, but gets pretty messy. And at that point, it is really convenient to say our stress tensor in some rotated coordinate system we can express with our orthogonal transformation as follows. Now, you can have now, essentially, you can start rotating the stress tensor, and we will do this in a second. I give you an idea how this looks like, and then I tell you why I can do certain rotations that lead to some beautiful results. I can rotate the stress tensor. In 2D, you only had to rotate your stress tensor slowly, follow the coefficients, and then essentially detect when you reach a maximum in the normal or a maximum in the shear stresses. In 3D, this is also possible, but now you have a little bit more like Rubik's Cube in your hand. You can rotate about 2 axes. And so finding these rotation angles that you have to apply from your original coordinate system into a coordinate system in which the stress tensor, let's say, has a maximum in the normal stresses where all the shear stresses disappear is more cumbersome, but it's still possible. And so what I want to show you, and then we will talk about what I did here in greater detail, because I'm cheating, I admit it up front. This is not what I do here randomly. It is, let me see, I think it was this guy. No, was it this guy? Which one is it? Okay, I know that this guy is working. Maybe it's the okay, here. So I can do this on both. So what I have here is a little MATLAB script. It's nothing, kind of too exciting, but I have a particular stress tensor, and I give you all the information later on, and you see kind of the stress tensor I highlighted here. This is my stress tensor, and this is my stress tensor with some numbers in my original coordinate system. I can obviously do something with the stress tensor, but we get there. what I want to show you now is here this super fancy plot. Okay, so this fancy plot is nothing else than a bunch of coordinate systems that we will slowly develop. And with these coordinate systems, I will express in the black axis, and this here is the green axis, which is also considered black in the black coordinate system, but I will rotate about always the axis that is green. I will rotate my coordinate systems, and so I will rotate a coordinate system, then I will rotate in the rotated coordinate system about another axis. So it's kind of getting a little bit involved. But what I want you to watch is, as I rotate the coordinate system from the original one, which I call x3, x2, and x1, which is the red one, I will now go and rotate the coordinate system and express the stress tensor in the rotated coordinate system. So what I do first is I will rotate my coordinate system about x1. This is why it's green. And so what you should see is now essentially I slowly rotate this about x1. So I hope you can see that this is rotating about the green coordinate system. And as I rotate this thing, these numbers here change. Interestingly is obviously that the 4 doesn't change because this is the 1,1 component in the essentially direction of the rotation axis. Okay, so I do this game and kind of the numbers change and they change. That's the main lesson to be learned. And then I'm kind of like Rubik's Cube. If you do it like me, it's kind of a random process. It's random walk. I have no systematic behind it. So I simply rotate this thing. And then I'm sick of it. And I go and rotate now about this axis. So the rotation axis is now not anymore one of my red axes in my original coordinate system. Now I rotate it about this one. And so you see kind of now the black axes are, still moving. But now watch at the components of my stress tensor, what happens to them. So at one point, I get a very interesting system where suddenly this guy takes a particular number, but what's more interesting is I don't have any shear stresses anymore. So I don't have a sigma 1, 2 prime, sigma 1, 3 prime. Okay? So what does this mean? We will talk about this in a second. And then I say, okay, maybe I like now this number here, and I don't want to change anything about this one. So now I go and rotate about, this is the axis essentially in which I have now my 1, 1, where this tensor looks pretty interesting. And now I start rotating about this guy. So now you see kind of this switches to green. I hope you appreciate my MATLAB skills here. And then, kind of we rotate this thing here until we get another interesting coordinate system. And now we have essentially rotated it until all the shear stresses vanish. Okay? So now that was, obviously you could have done this randomly, these rotations. I hope you also appreciate the rotation is not trivial because I didn't just rotate about x1 and x2 and x3. I rotated here about rotated coordinate systems. Okay? If you do it right, which I obviously did, but again, I admit it was not kind of sheer luck. I knew how to rotate this. Then you end up with a coordinate system in which your stress tensor looks, if you forget about the 3D aspect, but you look at the 2D, then you would essentially already conclude these are my principal stresses. Because when I have my principal stresses, in this kind of coordinate systems, all my shear stresses vanish. Is this clear? Now, obviously, what I didn't tell you is how the rotations are done. Because now we have the interesting fact that I rotate a coordinate system, which essentially really I rotate, I express in the rotated coordinate system my stress tensor. I never actually change the stress tensor. So the stress tensor, essentially, I didn't create a new stress tensor. I only used the original one and expressed the original one in different coordinate systems. What I, however, did here visually is I rotated axes. Okay, so I hope you appreciate the difference. The stress tensor never changed, but I created these red axes by rotating other axes. So I really kind of created new basis vectors. And so I intermingled these two processes, and this is what you get. Okay? So now we talk about how did I do this. And I hope that gives you some insight, and it's not really that difficult, but I know students typically struggle with it a little bit. How do I do it? And then we can talk about the definitions of the stress tensor. So again, you have the script. You can look at it. I will give you also another version, essentially how you can do it. There are different ways of doing the transformations. But let's first talk about essentially how do we find these coordinate systems in which we have these principal stresses. Okay? So obviously, when you can think of now, these principal stresses, they come with a particular coordinate system, and this particular coordinate system, what does this mean? Again, if you remember in 2D, we essentially could go, and we had our stress cube here, and then we started rotating it to a certain point. And let's say this is essentially where I have now my x1 prime and x2 prime. And this is by chance the rotation that gives me the coordinate system in which I have no shear stresses and where my normal stresses are principal stresses. I hope you see that these axes that I have, you can consider them as normals on planes. So here it's a normal on an edge. In 3D, obviously that's a normal on a plane. Okay? So now if these are normals on a plane, then I can talk about planes. Okay, so stress planes. And with this idea of planes, then we can essentially go and say, if I find a plane on which I have no tangential components of my stress vector, then I have found a plane where the normal of the plane points in a so-called principal direction. And I can also argue that the magnitude of my stress vector that is pointing now just in the direction of the normal, the magnitude is the principal stress. Okay, does this make sense? So in other words, what I'm looking for is, so for finding the principal stresses, which is related directly to the so-called principal directions. And this is then the normals on the principal planes. The mathematical expression for what we are looking at is if I take my Cauchy's formula, that gives me a traction vector. You can think of, we wrote this like this. And now what I want to have is that this traction vector has only normal components, which means I can write this as some value lambda times nu itself. Okay, is this clear? What problem does this get me? If I resort this equation a little bit, then I have here this guy minus lambda nu equals 0. Or I can write this as sigma minus lambda identity times nu equals 0. And what is this? What type of problem? It's an eigenvalue problem, obviously. So now we can essentially solve for the eigenvectors and eigenvalues. The eigenvalues, these lambdas, if I solve the eigenvalue problem, I will get how many eigenvalues? 3? Do I get always 3 eigenvalues distinctly different? No. Can I guarantee that the eigenvalues are real? When can I guarantee that the eigenvalues are real? And yeah. Okay, and the same obviously goes with the eigenvectors. So I want to obviously have eigenvectors that are also real eigenvectors. Okay, so the lambda i's, we will get the lambda 1, 2, and 3, and they will be my principal stresses, sigma 1, sigma 2, and sigma 3. For the sake of our discussion, it is very convenient to sort the eigenvalues such that in our discussion, we always sort them that sigma 1 is larger than sigma 2 than sigma 3. And not by magnitude, by the full value was the signed value. Okay? Yes?
So we said there was a principal plane, a single plane where there was essentially zero shear stress, but wouldn't 3 different unique eigenvectors mean 3 different planes? Would that be satisfied?
Yes, exactly. You get 3 different planes. Again, as this equation here says, and this is the key equation that explains everything, I will find eigenvectors on which which essentially the eigenvectors are normals on planes, and when I essentially compute the traction vector on these planes, the traction vector has only a normal component. So obviously, you will get 3 planes. Okay? So now you have to be careful with one thing. So what we can show, and I will skip this, is that the associated eigenvectors, so you can think of the new P, let's call this new 1. I have to check how I called them. I don't think I give them a particular name. So then these new 1s, new 2s, and new 3s, they are orthogonal to each other. Okay? So they in itself, you can think of them as spanning a Cartesian coordinate system. One word of caution is it is not simply saying, okay, new 1 is my, you can simply say, now, give me a second there. You can simply go and say, okay, this is essentially now my E1 prime, and this is my E2 prime, and this is my E3 prime, okay? That's a little bit tricky. You cannot do this automatically because what can go wrong? Does anybody see what can go wrong? So these new 1, 2, 3 are orthogonal to each other. So you say, oh, that's great. This is like a Cartesian coordinate system. There's one catch to it, a slight catch.
There can sometimes be non-uniqueness.
No, the real issue is, it's a simple one, is it's not necessarily a right-handed coordinate system that you get this way. So you have to typically go and make sure that if you do, let's say, new 1 cross new 2, you will either get plus or minus new 3. And so if you want to work in this coordinate system, you don't want to go into left-handed coordinate systems, but you want to keep on working in a right-handed Cartesian coordinate system with this, you might have to essentially flip the sign on the new 3. But it doesn't really matter from a physics point of view because it's just essentially reorienting the norm. But that can screw you up if you don't do this correctly. Okay? So now what we can obviously do, and that leads to something that you will, especially if you take more advanced courses than this course, have to get used to, is that the eigenvalue problem that we write, we can simply write it's an eigenvalue problem. How did you learn to solve these eigenvalue problems before MATLAB? Today my eigenvalue problem is solved with Ike. So there is not much more to do it. But what was the original idea when you did this in high school or in calc?
Characteristic polynomial.
You get your characteristic equation. Now, this characteristic equation, obviously, if you write it out and you simply do what you learned in high school for a 3x3 matrix, is you get here a bunch of stress components in this thing. Now, the interesting way of writing this eigenvalue problem, and I think you can appreciate it very quickly, is you could simply get an eigenvalue problem where I now go and simply replace the lambda with what I call sigma p. It's simply the principal stress. And my characteristic function or equation for the eigenvalue problem can be written in the following sense. It's a sigma p cubed minus I1. Then you have seen these i's before. Sigma principal squared plus I2 sigma p minus I3 equals 0. So do you remember what did we call I1 and I2?
Variance.
These were the invariants. Now, we had only 2 invariants because we were working for a 2D stress tensor. Now we have a 3D stress tensor and we get 3 invariants. I write this down for 2 reasons. First of all, it's very clear since the principal stresses do not depend on the coordinate system, they're always the same, the principal stresses. There is a particular coordinate system in which sigma 1, 1 is one of the principal stresses. But still, the principal stresses are physics. This is physics. It doesn't depend on the coordinate system. So obviously, the governing equation for giving me these principal values need to be able to expressed in quantities with factors that do not depend on the coordinate system. Otherwise, that would not work. Is this clear? So therefore, very interestingly, I can write the characteristic equations for the principal stresses with respect to my invariance of my stress tensor. So I like this to show because now you understand, hopefully, why principal stresses are also invariants. Because they are the solution of an equation that depends on the invariance. Does that make sense? It's a little bit kind of a circular argument. Yeah, it's absolutely a circular argument, but sometimes people don't get why principal stresses are invariants because of the argument I only get them if I choose a particular coordinate system. That's more kind of an illustration what this physically means. Mathematically, there are invariants, and the explanation why there are invariants is exactly this characteristic equation. Okay, so now we have to define the invariants. We define them for the 2D case, so it's pretty much an extension, so it's the trace of the stress tensor is I1. I2 is the summation of the subdeterminants. So you get here essentially then sigma 2, 2, sigma 2, 3, sigma 3, 2, sigma 3, 3, plus sigma 1, 1, sigma 1, 3, sigma 3, 1, sigma 3, 3, and plus sigma, which one do I miss? 1, 1, sigma 2, 2, sigma, sigma 1, 2, sigma 2, 1, sigma 2, 2. Okay, so I can obviously write this nicely in index notation, and that's something you might need for your homework if you haven't started it yet. So this is sigma I, sigma jj minus sigma ij, sigma ij. Okay, And the third one is actually the easy one. It's the determinant of sigma. Yes?
Is that universally true for an eigenvalue, eigenvector problem, or is that strictly for the stress?
It's universal. There's nothing particular.
I feel like I never learned that in undergrad. Would have been super useful.
Yeah, but this is why you pay the tuition.
So I just had to wait like graduate year to learn this.
This is like you buy a car and the nice seats you get only for an extra cost. That's how you can think of grad school. Okay. So obviously these things become very simple if we have the stress tensor in principal. If we know the principal stresses, because then obviously this is sigma 1 plus sigma 2 plus sigma 3. The second equation becomes also pretty simple, so that's essentially going like this. So this is sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. And this equation becomes the sigma 1 times sigma 2 times sigma 3. Okay, so that's also actually very, very helpful. We will later learn that these invariants, again, they contain physics. And therefore, these invariants are very often used to model physics. Again, if I say, for example, I want to describe the stress-strain relation, which is, we will learn this, and you have seen this before, the stress-strain relation has to do with the material, so this is what we call the material, the constitutive law. It's very nice to work in invariants because they contain the physics. It would be actually ugly, again, to go through the pain of doing this for a particular coordinate system because I would have to change my constitutive law for the particular coordinate system I work in. So writing them in invariants looks at the beginning very messy, but it's actually much more meaningful because you kick out the dependency of a particular coordinate system. Now, there's one thing where, and you have seen this before, where in order to illustrate what is going on, some people still like to use Mohr circle. But now, and I could go back to what I showed you with my little MATLAB script, is remember at one point in my MATLAB script, I had a coordinate system where I had already found that my x1 axis, there was essentially one value up in the left and in the upper row all zeros except for the diagonal term, and the left column all zeros. So we had something that looked like sigma 1, 0, 0, 0, 0, and then there were some non-zero entries here. So what is this stress tensor at this point? At this point, I have revealed a plane in which essentially the normal to this plane, the traction vector will be just sigma 1 times the normal itself. Okay? But that leaves me now, essentially I have now this plane, so you can think of, I have now this plane. This is this plane. Here is my normal vector, but then I still have some ambiguity how I oriented my coordinate system within the plane, and this is what I did in my third rotation. I essentially froze this thing, and then I rotated about my pen here. Okay? And now I can essentially play in this plane, which is nice, because this is now reduced to a 2D problem. I can play the rotation game, but this rotation game can be nicely illustrated with Mohr circle. Okay, so within this plane here, so this you can think of is now a 2D problem here. This here is a kind of a 2D problem. Not anymore in your original coordinate system. This is now in this already rotated coordinate system. And now I can go and play here the game of Mohr circle, which means if I plot the normal stresses and the shear stresses, then I might have somewhere sigma 1, but then I can construct a Mohr circle somewhere here. And this Mohr circle will reveal that I have sigma 3 here and sigma 2 here. Okay? Does this make sense? So essentially, this here is your classical Mohr circle in this plane that has a normal that has the eigenvector associated with sigma 1. Okay? Now you can obviously play this game in different forms. You can go now and simply argue, okay, I can go now and say, okay, my eigenvector, my sigma 3 here, this is now my normal, and I can construct a Mohr circle that essentially looks like sigma 1 and sigma 2 here. And I can also go and have the same thing with sigma 3, sigma 2, and sigma 1. And now I have a normal that is in the eigenvector associated with sigma 2. And my should-be circle looks like this. Okay? Now, obviously, when you look now for in each of these planes, I will be able to reveal a maximum shear stress. So there is essentially my maximum shear stress here. There is my maximum shear stress here. And there is my maximum shear stress here. Okay? Now, this is for each individual plane, but my overall maximum shear stress is obviously the one, because you can see easily that the magnitude of the shear stress is just the two principal stresses in the plane divided by 2, or the difference between the two principal stresses divided by 2. So which one is the biggest difference? It's obviously, if we use our notation, sigma 1 larger than sigma 2, then larger than sigma 3, this is this one. So this here is the maximum total. So we can directly conclude that tau max will be 1/2 sigma 1 minus sigma 3. There's a famous catch to this. You know, as if I give you a 2D stress tensor, what do you have to watch? What is your maximum shear? If I give you essentially a 2D, you always have to think of, if I give you a 2D stress tensor, it simply means that sigma 3 is 0. Okay? So in order to figure out what my tau max is, you want to consider, let's say I give you this guy and I give you this guy, and this guy sigma 3 would be 0. And so your maximum shear stress is not sigma 1 minus sigma 2 divided by 2. It's actually sigma 1 minus sigma 3, which is 0, divided by 2. So it's sigma 1/2. Okay? So only to make sure that you get this situation, which is actually really crucial for practical applications. So if you have something like this, where, let's say, sigma 3 sits here, sigma 2 sits here, and sigma 1 sits here, you can typically, you make all your analysis just in the x1, x2 plane. And you say, okay, now I know how to get my shear stress. Yeah, my maximum shear stress here is this value. So it is essentially here sigma 1 minus sigma 2 divided by 2. But that is incorrect. Your maximum shear stress, even if you assume that sigma 3 is 0, is still associated with the Mohr circle. That is this one, which is sigma 1 divided by 2. Only that's if I tell you the story like this, then, where's the catch? That's one of these things, if you don't know, if you don't remember this, you easily make a mistake. And this mistake can actually be really catastrophic. And it's very easy to make this mistake. Okay. So this is now how you can do all these things, and how the principal stresses can be looked at, and how you could still reduce the problem to essentially a sequence of 3 two-dimensional problems. So you can cut down the 3D problem in a sequence of 3 two-dimensional problems. However, and now I wanted to explain a little bit what my example did, what I did with my example, and why I cheated in this example. And that is maybe of some interest also with respect to the homework. Okay, so I started with my stress tensor. I got an email about this notation. Typically, and I apologize if this is not completely, kind of always follow this rule, when we put these things in square brackets, which could be this notation or this notation, what it typically means is that we write the tensor in matrix form. For kind of rank 1 and rank 2 tensors, not a big deal. If we go to higher order tensors, it is actually a big deal for a rank 3 and rank 4th tensor. Kind of if you see suddenly this construct that looks like a matrix, you have to be aware of what convention was used to so-called flatten the matrix into a matrix, the tensor into a matrix. So therefore, some people like this notation. For rank 1 and rank 2 tensors, you can typically skip it. So we had essentially this problem 4, 3, 1, 3, 2, 1, 1, 1, 5. So this was my tensor. If you want to add, units, be my guest. I have to admit that since my research is a little bit more on the math side, I have the tendency to skip units, which typically bites you at one point, because then you have to make an argument why your example works with a Young's modulus of 1, and you get kind of absolute nonsense values. But so do units, it typically prevents you from getting in trouble, even if it's not really about units. Okay, so what we can do now with this tensor, obviously, is we can just compute the eigenvalues. Okay, so you get eigenvalues, and for this one, you got 7.1, sigma 2 was 4.1. I write these numbers down because I want to show you, if we have time, the animation again. Okay? Obviously, you can now go and compute your tau, your shear stresses, and so your tau max in the different planes is, so in the 1, 2 plane is 1.5, tau 2, 3 is 2.1, and tau 1, 3, which should be the maximum one, is 3.6. Okay. So now what did I do is I wanted to construct a coordinate system by essentially through a sequence of rotations where my x1 axis becomes the first eigenvector or the eigenvector associated with sigma 1. Okay? So in other words, what I had is I wanted to have here my original coordinate system. This is x1, x2, x3. And I knew that there is somewhere which I computed with Eich or by hand. With Eich or by hand, I had somewhere here I call it x1s. This is the direction, and you can think of this as my first eigenvector, but it's a normalized first eigenvector. Okay? So in order to go now and construct a rotation, and again, you could have skipped the rotation. You could easily have written this directly in the coordinate system of the eigenvectors. But I wanted to go through this idea of I go through a rotation and I rotate until I find these extreme values. What I did first is I constructed a third vector, which I called XR. And XR is nothing else than E1 cross E1s. Or to be more consistent, let's call this ER. So what does this, why is this useful? Because now I can guarantee that ER is perpendicular to x1. So what I did is essentially in my first step, I took x2, I essentially went and rotated about x1, x2 into ER. So that's a rotation. Okay? Clear?
Perpendicular or just in plane?
So x1 is perpendicular to ER, and since I know that because of this perpendicular, I know that ER is in the plane, in the x2, x3 plane by construction. Okay, this is the reason why I can guarantee that by rotating x2 about x1, I can get into ER. Okay? Once I have this, now I can rotate in my second step. So this was my step 1. In my second step, I rotate now x1 into x1s. And then in my third rotation, I rotate about x1s. Okay? I rotate about x1s. Yes?
Yeah, can we please just repeat it very briefly again?
Yeah. So in my first step, I went and rotated, and then I can show the animation again. I rotated x2 into ER. Again, the ER is my cheating point. Because about x1.
Okay.
So I rotate x2 about x1 into ER. Again, why do I know ER? Because that's where I cheated, because I first computed the eigenvectors. And so I knew essentially that I could create ER by the cross product with essentially between E1 or x1 and x1s. Is this clear why this is what I call cheating? That is where I took away the randomness of my rotations. Because then I knew that ER is something that I can use to rotate x1 into x1s. Obviously, it's only for illustration purposes. You could have asked, directly use x1s and you're done, but then we didn't have this nice rotation where you saw the coefficients of the tensor changing. Okay, once I do this, then I rotate once I rotate x1 into x1s, now I'm at this point where I have my stress tensor. So essentially after step 2, I have a stress tensor in my coordinate system that has here sigma 1, 0, 0, 0, 0, and something. Okay? And now by rotating in step 3 about x1s, I can change these numbers here until I get a strict diagonal stress tensor. Is this clear? Again, this is why I gave you the MATLAB script. Play with it. If you don't see it, this is why I wanted to give you the MATLAB script. But I hope that takes away all the mystery of what it really means of rotating stress tensors and how do I get into a coordinate system with principal directions. But this is all. So I have 3 steps. The first one is the one that I need to do the right rotations. The second one gets me x1 into x1s. And once I have x1 into x1s, I have this form. And now with step 3, which is a rotation about x1s, with step 3, now I get this thing into sigma 1, sigma 2, and sigma 3. Okay? I did a little bit of cheating here again. I selected my rotations exactly such that I get sigma 1, sigma 2, sigma 3. You could have also got sigma 1, sigma 3, sigma 2. Okay? That's it. So only to show this again, and then I hope you can follow this exactly what we're doing here. I run this thing again. So you see here, these are the principal stress values that I computed. These are the shear stress values that I computed. And this is now where we start from. Maybe a little bit bigger. And now again, I go and rotate first about x1. Okay, so let me do this. I rotate x1 until I hit that x2 is this ER vector. Okay, this is now when I have the position. You see the stress tensor at that point is still a mess. And now I start rotating about x2 prime. And now you see kind of I move my x1 direction until I hit the point where I get zero shear stresses here. Then I essentially freeze this, and now I have the situation where I just rotate about x1 until all the other guys become 0. And then you see I have here my principal stresses on the diagonal. Is this clear? Good. Again, how did I do this now mathematically? And it's actually very, very simple. You can, once you know the coordinate system, your rotated, the basis vector of the rotated coordinate system expressed in the original coordinate system, I can construct our orthogonal rotation tensor, and then I simply perform the rotation. Now there is a little bit of an interesting way of looking at this. Yep. So there is an interesting way of doing this, and I will talk a little bit about more on this on Friday, but because I know you need it or you have the homework due only on Monday, so that's good news. How do I do rotations about an arbitrary vector? Okay, so let's say I have something and that helps in terms of, so I want to rotate something about an arbitrary vector, let's say R. When I say something, it could be another vector, it could be, kind of something, a tensor or something like this. The simple idea is to, and this is where coordinate transformations and rotations play together, and that's the key that I want you to understand, is that we can easily express rotations if in a coordinate system where the rotation or the vector about which we rotate is one of our basis vectors. So for example, you all know that this orthogonal tensor, if I rotate about the third basis vector, looks like, I simply, you know what I mean. If not, I'm happy to write it out.
Minus.
Okay.
There's an extra minus on the 2-1.
2 minus signs.
Oh, sorry. Yes. Okay. Sorry. Thanks for catching this. So you know that this is easy. This is an easy rotation that expresses a rotation about my third basis vector. So I want to rotate about R, but r is not one of my basis vectors. So how do I use this simple tool to do the rotation? I will simply construct, and you can see later on, once you know how it works, you put this all together and it's very simple. I simply say, okay, I make this here my x3 prime. Okay? So I will build a coordinate system that has my r, my x3 prime, and I will construct essentially an x1 and an x2. So let's say this is my x1 prime. Oop. This is my x1 prime, and this is my x2 prime. And now what I can do is I can easily, in this prime coordinate system, I can perform the rotation. Okay? So I can, in the prime coordinate system, construct a rotation. However, I first have to go and express whatever I want to rotate in the prime coordinate system. I do the rotation, and then I pull it back in my original coordinate system. I will work this out on Friday, but that gets you hopefully thinking about how to do this. Once you know how to do it, you will simply see that I can combine essentially these two transformations. The one is essentially a coordinate transformation, and the other one is a real rotation. I can combine them in one matrix, and then I can write down these kind of operations in a very compact form. Okay. Thanks, and again, I apologize for the inconvenience about the office hours, but simply drop me an email or stop by my office, and I'm happy to help you out with any questions you have.